within the liquid argon. So liquid argon has a high cross-section area where it can actually interact with neutrinos. So when the neutrino interacts with argon, it generates a charge. Then it's in the field, so the charge drifts, picked up on the wire. That charge is collected by the ASICs. The ASICs will amplify and shape the charge, which then gets sent to an ADC. ADC samples the data, which then goes into another ASIC where it takes all the channels of information and streams it up to a board which collects it and sends it to a data farm eventually. So actually, I should have these slides backwards. So let me start with this slide first. So they showed you all the ASICs. So I believe they spoke to you about the LAR ASIC, which is the preamp shaper, which Nara, I believe, I don't know if he showed that information. So this is the ASIC that collects the charge. The chip above it is an ADC, which samples it at 500 2 megasamples per second, 500 nanoseconds. That data is then read out by these two ASICs up here, which aggregates the data, multiplexes it over a high-speed link, which transmits the data over a 1.25 gigabit links being sent out of the cryostat to the outside world. Actually, I'll show you these. So during the walk, I'll show you these boards. So this board here actually has 18 ASICs. So we have 8 LAR ASICs, 8 ADCs, and the 2 Coldatas. It reads out 128 channels, and it pretty much it samples the 128 channels at 2 megasamples per second, and just continuously streams the data out to the outside world. Now, the cool thing about this is that this is in the cryostat. Now, these boards are all over this cryostat. Now, these cryostats are enormous. I mean, literally, you can fit a house inside one of these cryostats. I mean, it's insane the amount of liquid argon is in there. In order to take this data out, we're transmitting it over these 1.25 gigabit links. The scary thing is, I don't know if you guys know, transmitting data at 1.25 gigabits, normally when you have that much data, you want to use fiber optics. However, we couldn't find a transceiver that worked with low enough power, that worked in liquid argon at those temperatures. So we are transmitting these data over 25 meters of cable of copper. So there was a lot of testing to figure out how to actually get this data out, looking at the characteristics of all the different cables, coming up with the proper drivers to be able to transmit the data out of these ASICs to the outside world. So this was years and years in development and getting this board to work. So the crazy thing, again, all this electronics is working at minus 28 degrees Celsius. One of the interesting things, before we got to the final version, which you're seeing here, I spent years working with cold FPGA. So before we had the readout, the way of reading out the data using these ASICs, I was using an FPGA in liquid nitrogen or liquid argon, and got it to work at the minus 180 degrees Celsius. So it's pretty much I had to test every FPGA on the market to see if any of them worked and to see if the transceivers work, power up. It's insane.
Was that like a like just testing like kind of like your own like not like literature survey, but like kind of like you just going through and like testing on the boards?
So what he's doing is he's doing like a validation in Bringo, right?
Yeah.
Design something, put on the board, and then go test it and bring it up. Right?
But you said it did that with like multiple different boards, like
because they build multiple different.
No, I mean like he was doing that with like different types of FPGAs to test it.
Well, yeah, we were looking at like commercial FPGAs because we don't.
This is Harel's one of Harel's PhDs. So you tested a lot of different FPGA boards before you decided on that. And did you just buy the parts, or did you actually buy the dev boards?
Okay, so here's the problem. Electronics do not like to work at minus 180.
Right. But actually, one of the Kintexes is actually pretty good at low temperatures, right? Though one of the 28 nanometer Kintex.
Actually,
There's a couple of papers where they've actually used one of the Kintex parts in a deep fryer.
I'll be honest. The 28 when I was doing the study,
Mm-hmm.
they weren't the 28 nanometer Kintexes weren't available.
This stuff was over a very
The
long
Ultra Scale
period.
Plus.
Yeah,
So
it's
where
on
did you
the
start?
scale.
What's that?
Which parts did you start with?
Uh,
And did you actually buy the boards, or did you just
okay,
get the parts?
Okay, so the thing is, you can't use dev boards.
Okay, so you just bought the parts.
Well, I had to test every different FPGA because most FPGAs don't work in liquid argon or liquid nitrogen. The other problem is when you put them into those temperatures.
Mm-hmm.
I would say most of the regulators don't work at those temperatures.
Right.
And the components, oscillators, nothing works
Right,
at
nothing's
minus
going to work
180.
at minus.
So you really can't use dev boards.
So you just bought the parts. That
What's
was
that?
The question was you
Well,
bought the FPGA
okay.
parts. Just the
Themselves?
chips themselves, the part.
So it depends. So sometimes we bought dev boards,
Mm-hmm.
which we completely ripped apart,
Mm-hmm.
took off all the regulators and bypassed everything, and we completely retrofitted it to work in cryo.
Okay.
Other boards, we actually did build the actual board itself just to test it in cryo.
Mm-hmm.
So it was a combination of both.
Okay,
So
I got you.
so we did buy dev board, but right out of the box, no dev board will ever work.
No, they
In
don't,
cryo.
because they're not even designed. Some of them don't even work in. Some of them don't even work if you just plug them in, stick them in a
No.
computer or whatever. But yeah.
Yeah,
But anyway, which part did you just use Xilinx parts?
No. So for this, we actually used a Altera Cyclone 4.
Okay.
So
Yeah, you were in trouble.
and why's that?
They're not the best parts in the world, but go ahead. They're not
Well-
the best boards in the world, but go ahead. They've got a lot of bells and whistles on them that are useless, but go ahead. They've all got Cyclone 4s, by the way.
Oh, okay.
Well,
But anyway,
wait. So the dev board you're having these issues, or the FPGA? Because I'll be honest, I'm partial to Intel Altera versus Xilinx.
Okay.
I'd take a Xilinx over an Altera any day.
It gets spicy.
Any day.
Really?
But that's simply because what the fabric looks like.
Well, my biggest greed with Xilinx is their software.
I'm not
they're-
fond of Vivado. I actually still prefer to use ISE than Vivado because Vivado is. I don't even know what the difference is with
Okay.
Vivado. I just don't know.
But, no, I use both, and if I have a choice, I would honestly prefer Altera.
So I don't like
But that's a personal preference.
Well, the reason why I don't like Altera is if you look at the fabric and the actual architecture of FPGA, it looks much more like a CPU. And I'm a raw logic designer. So I just want logic. I don't want any bells and whistles in
Okay.
the fabric. So I like Xilinx.
Well, I have to say, I mean, I do agree that the hardware, Xilinx's hardware is better. I cannot, hands down, they definitely have better hardware. However, their user experience in terms of their software is so horrible that I prefer to go with Altera
I got you.
because if you spend one day writing code and the next week fighting the tools, it's a waste of time.
You know,
That's-
ISE used to be very intuitive and easy
Yeah.
to use, and then they came up with Vivado, and a lot of the newer parts you can only use Vivado. And Vivado is just trying to find a simple piece of time and information can take you like 6 weeks.
Yeah.
So yeah, I'm totally with you on the tools.
I mean, if it wasn't for the tools, I completely agree with you. But I mean, the worst thing, you make a simple typo in Vivado, you have to go. It goes through the entire compilation. You're talking about hours, and then it says, "Oh, you forgot to put a semicolon." Are you freaking kidding me? You know, that happened to me so many times. It really, where Altera just here syntax error. But okay, that's another story. So anyhow, so this is the Cold Electronics, This has to send data to the outside world. So this, like I mentioned, has 1.25 gigabit links. That gets transmitted to a flange. Behind the flange, so on the other side of the flange, we have a board which I'm really proud of this board. This is actually a Xilinx. You'll be happy about that.
The Ultra Sync.
It uses a Xilinx Zynq UltraScale Plus. I don't know if you guys are familiar with that.
Yeah.
Yes, very recently familiar with it.
Okay, so this board can interface up to 4 of those FEMDs what I showed you.
Well, up to 4 of.
So 4 of the cold electronic boards. So this one board plugs into the backplane. It has 4 cables coming out of the flange going to each one of those boards. This controls the power, so measures power, current, slow communication, the high-speed links to those boards. This is running the UltraScale Zynq UltraScale Plus, so it's running Petalinux, where we have a server running over there, communicating and controlling the whole board. It's a fun board, especially since you have you SSH into this board and you can control the whole experiment that way.
Right.
So it's a fun little board. This is on the back end at the room at room temperature, and then it has 2 10 gigabit links which communicates to the data farm. Right now we're talking to a board called Felix board, which I'll talk about as well. But I think we're going to probably switch over to a UDP interface to get rid of any type of proprietary readout boards later on. If you can go with a commercial solution.